we're doing light reflection and refraction chapter. We have finished reflection part in this chapter, and now we are moving to refraction part. So today we will see about refraction, refractive index, and the rectangular glass slab experiment. So what is refraction? When you see this glass, a pencil is immersed in it, but there is a break. There is a break here. It seems to be, there is a pencil, there are two pencils, there are two parts of the pencil, but actually the pencil has to be like this, right? Why is it so? Why there is a break? We know that light travels in a straight line, but is this a straight line? There is a break or there is a bend, right? So whenever there is a, whenever there are two mediums, this is an air medium and this is a water medium. Whenever light travels from one medium to another, there is a bend. There is a bending of light. So what is refraction? Light bends when traveling from one medium to another. When it goes from one medium to another, the light rays bend. Okay, so this is refraction. So like the laws of reflection, we have laws of refraction. Okay, so before that, we know that this is a refracting surface. There it was a polished surface. This is a refracting surface. And what is this green line that we have? Yes, it is normal. We denote it as N. This line is the angle of, this line is the incident ray. Okay. And when the incident ray comes near the refracting surface, there are two mediums, that is medium 1 and medium 2 for a refraction to happen. There are two cases for the incident ray to go after refraction. So the refracted ray can go like this or like this. That is, the refracted ray can go towards the normal, or the refracted ray can go away from the normal, towards the normal and away from the normal. So the laws of refraction states that the angle of the incident ray, the refracted ray, and the normal lie in the same plane. Okay, this is similar to our laws of reflection. Correct. The second law is the Snell's law, given by a scientist named Snell. He said that the ratio of sine of angle of incidence to the sine of angle of refraction is a constant. Ratio of sine of incidence to the sine of angle of refraction is always a constant. And this constant is called as refractive index. Refractive index. Okay. So are you clear about this? Similarly, we have the same thing that we have in our reflection. There are two laws in reflection. Likewise, we have two laws in refraction. The first law is the same. The incident ray, the normal, and the refracted ray here lie in the same plane. The second law is the Snell's law, that is the ratio of sine of angle of incidence to the sine of angle of refraction is a constant. And this constant is called as, yes, a refractive index. Does refractive index has a unit? Yes or no? No. It is a constant, so there is no unit. So refractive index for different medium will have different refractive index. Good. Okay. So we will now see what is the refractive index. Now, refractive index, we said it is a constant and it is usually denoted by N, or you can denote it by mu. Okay, mu. Now, refractive index of the, how to calculate this refractive index? There should be some formula. So, refractive index of the first medium with respect to this second will be the velocity of second, the velocity of light in second medium divided by the velocity of light in the first medium. This is the refractive index of first medium with respect to second. Similarly, there should be refractive index of the second medium with respect to the first medium. Okay, so it will be B1 by velocity of light in first medium divided by the velocity of light in the second medium. When one of these mediums is air or vacuum, when one of this medium is an air or vacuum, we say that the refractive index calculated by this part will be the absolute refractive index. Absolute refractive index of that medium. Let's say we are taking a refractive index of water with respect to air or vacuum. Then that will be the refractive index of absolute refractive index of water with air or vacuum will be the absolute refractive index. Okay. So this refractive index of water is 1.33. Refractive index of air is 1. For glass, it is 1.5. Okay, it goes on. For different materials, it will have different refractive index. But then this refractive index will decide the velocity of light in that medium. So whenever there is a higher refractive index, higher the refractive index, higher refractive index, higher will be the density of the medium. When there is higher density, when it is so dense, can you move into a very crowded bus? It's like that. It's so dense. It's very crowded and it's in a peak hour. You can't go in, right? So whenever there is a higher density, you have to slowly go in. Okay. So whenever there is a higher density or higher refractive index, the velocity slows down. Velocity of what slows down? Velocity of light slows down. Okay. Velocity of light slows down. We can also write this refractive index as C by V. N is equal to C by V with respect to air or vacuum and the velocity of light in that medium. Okay. So I hope you're clear with this. Whenever there is a higher refractive index, there is higher density and there is slower velocity. Good. So for different mediums, it will be different. The refractive index will be different. That is the crux of this one. Okay, now we'll experimentally do something and find out what will happen when the light rays hit a rectangular glass slab. So we take a rectangular glass slab and name it as A, B, C, D. And these are my normals. Okay, so I name it as M, N, and M dash and N dash. Now, there is a light incident on this. There is a light ray. Let's take OP incident on this. And this point as E. I take this point where it meets the rectangular glass slab as P. Now, this is an air medium. This is a glass medium, right? So it moves from glass is denser or rarer than the air. Glass is denser. Okay, glass is denser than air. So when we draw when the light passes through this rarer medium to denser medium, this is a rarer medium. Wherever it is lower refractive index, it is a rarer medium, and higher refractive index is a denser medium. It bends. Refraction happens. Okay, it bends. Let's say this line inside the glass slab to be x and y. This point, let's take it as f. Okay, this bends, and this is the angle of incidence. Okay, this is the angle of refraction here. And when this bends like this, it bends towards the normal. Whenever it goes from a rarer medium to the denser medium, it goes towards the normal. Normal is our green line, right? So it goes towards the normal. And now again, here it is glass. It has to come out. The light ray entered inside the glass, has to come out. This is air. It comes out from denser medium to the rarer medium. Good. So when it comes out from denser medium to the rarer medium, it goes away from the normal. But your light ray should have come like this. The dotted lines. From the properties of light, it should have directly come without any bending. Why this bending happens is because the light ray incident on the glass slab is oblique, is at an angle. Okay, what will happen if it comes directly? What will happen if it comes directly normal to the perpendicular to the glass slab? There will be no deviation at all. There will be no refraction happening, and it will directly come out of the other side of the face. Okay. So, and always, if you see this is the emergent ray that we call, or the refracted ray we call. Let us take this as Q and R. This Q and R is always parallel to O and S. Q and R is always parallel to O and S. It is always parallel. Okay, why is it parallel? Because the opposite faces of this rectangular glass slab is parallel to each other. Okay, that is why the refracted ray, the QR and OS are always parallel. Okay, and you can see that this QR and OP is also the same. It will come out the same. That again, the reason for this same inclination will be because of the two opposite sides being parallel to each other. So whenever there is a light ray coming from a rarer medium to the denser medium, it will go towards the normal, and denser medium to rarer medium, it will go away from the normal. Okay. So this is how the rectangular glass slab works, and that is the conclusion. Whenever we go rarer and denser, optically rarer and optically denser mediums, the behavior of light will definitely change. Okay. So with this, we'll go to some questions. So we have the first question here. It is being asked in 2018 question paper. So the laws of refraction of light, explain the term absolute refractive index of a medium and write an expression to relate it to speed of light in vacuum. So what is the laws of refraction of light? There are two laws. The first law states that incident, normal, and refracted ray, correct, lie in the same plane. The second one is, yes, so the Snell's law, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant, and that constant is called as refractive index. The second question there is, explain the term absolute refractive index. So absolute refractive index can be defined as the refractive index of the medium with respect to air or vacuum. And what can be written? What is the expression that we wrote? C by V. We wrote it, right? Absolute refractive index C by V, because C is the speed of light in vacuum or air, and V is the velocity of the medium, speed of velocity of the light in that medium. Okay, yeah. Okay, the second question, interesting one. How should a ray be incident on a rectangular glass slab so that it comes out from the opposite side without being displaced? So there is no displacement, that there is no change. Okay. So when will that be? I told you now. Yes, whenever the incident ray is just perpendicular to this rectangular glass slab. It just comes out without getting any displacement or where any refraction. It just comes out. Okay, so this is the, whenever the incident ray is 90 degrees or perpendicular to the rectangular glass slab, the light ray does not have any displacement. Okay. Yeah, we'll now move on to some problems. A ray of light traveling in air is incident on the plane surface of a transparent medium. The angle of incidence is 45 degrees and the angle of refraction is 30 degrees. Find the refractive index of the medium. So what is given first? Angle of incidence is given. So I is 45 degrees. Angle of refraction is given. R is 30 degrees. Good. R is 30 degrees. What is to be found out? Refractive index of the medium. So I can write N. How can you find it out? What is the formula? Good. Sin I by sin R will be N, the refractive index. Okay. So what is sin I? 45. Sin 45 divided by sin 30. Go back to your trigonometric ratios. So what is sin 45? It is 1 by root 2 or root 3 by 2 or 1 by 2. It is 1 by root 2. Okay. Then what is sin 30? Is it 1 by 2 or root 3 by 2? There's always a confusion between sin 30 and sin 60, right? It's 1 by 2. Good. 1 by 2. So just simple mathematical operations. We will take it to the next one, reciprocal it. So 2 can be written as root 2 into root 2 divided by root 2. So this root 2 gets cancelled and the refractive index will be root 2. So N is equal to root 2, which is, what is the value of root 2? Any guesses? Yes, it's 1.414. Okay, it's 1.414. So I hope you're clear with this. We'll go to the next one. Find the refractive index of glass with respect to water. The refractive indices of these with respect to air is 3 by 2 and 4 by 3 respectively. So what is given now? Refractive index of glass with respect to air is given. That is 3 by 2. Okay. Then refractive index of water with respect to air is given, which is 4 by 3. But what do we want? What is to be found out? We have to find a refractive index of glass with respect to water. What will happen? Okay, so glass with respect to water. We know these two, right? It is very easy. So refractive index of glass with respect to air divided by refractive index of water with respect to air will give you the refractive index of glass with respect to water. So 3 by 2 divided by 4 by 3. So we will have 3 by 2 into 4 by 4, 3 by 4. Right? To be the reciprocal, it will be 3 by 4. So 9 by 8. So refractive index of glass with respect to water will give you 9 by 8. Yes. 9 by 8, you can still simplify. Okay. Okay. So moving on to the next one. The refractive indices of water and glass are 4 by 3 and 3 by 2 respectively. Find the speed of light in each. So we have been given N with diffractive index of water to be 4 by 3. We have to find the velocity of light in water. We know velocity of air or vacuum is 3 into 10 power 8 meter per second, right? Yeah. So N is equal to C by V, we know. We want V, C by N. So it will be 3 into 10 power 8 divided by 4 by 3. V is equal to 3 into 10 power 8 into 3 by 4, which is 9 by 4 into 10 power 8 meter per second. But still you can reduce this 9 by 4 and it will be 2.25. Okay, 2.25 into 10 power 8 meter per second. Very important. The units are very important. Okay. So this will be the velocity of light in water. Now, similarly, we'll do it for glass. Yes. So N will be equal to, N of glass will be equal to 3 by 2. Right? Okay. So C is again 3 into 10 power 8 meter per second. So V will be equal to 3 into 10 power 8 divided by 3 by 2, right? This will be 2 by 3 into 10 power 8. So velocity of glass will be 2 into 10 power 8 meter per second. Can you see the difference? In air or vacuum, it was 3. The velocity of light was 3. When it came to water, it reduced to 2.25. And when it went to glass, it again reduced to 2. So, can you see the velocity coming down with higher the refractive index or higher the density? The velocity slows down. Good. Yes. So, I hope we are clear with what is refraction, what is refractive index, the rectangular glass slab experiments, and the rarer, optically rarer medium and optically denser medium. Whenever the higher refractive index, there is always slowing down of the velocity and higher the density. So all this, we'll use these concepts in the next class with the spherical lenses and image formation in the next class.